collaborators from CMU. I'm very thankful for all of their support throughout these two projects. Some of you may know Chavi. She is also a visiting researcher here. She'll be back later this week. And I worked with her on the first project that I will be talking about in this talk. Okay. So we're all here because we are interested in collaborative learning. A primary motivation for collaborative learning systems is that they enable us to learn from siloed sources of data. So they enable data owners to indirectly share their data. So instead of directly sharing raw proprietary or private data, they can indirectly share this in the form of model updates, aggregate statistics, or some synthetic data. However, even though data sharing is indirect in collaborative learning systems, there are several factors that limit the adoption of these systems. And so last year, earlier, we conducted an interview study where we talked to 21 experts across organizations that are attempting to use federated learning in real-world problems in healthcare and finance. And one of the quotes that stuck out to me during these interviews is the following. So what federation, and this refers to federated learning and collaborative learning in general, what federation forces you to do is to think upfront about what is exactly going to happen, and then reverse engineer the technical stuff to make sure that outcome can happen. And to give a bit more detail into what this means, the results of federated learning and machine learning are, in general, difficult to predict. So for example, in the interviews that we conducted, all these organizations pursued federated learning because they knew, due to their own domain expertise, that the data that they had was insufficient to train a good model. And they also knew that other organizations like them had the data that they wanted. Another factor is trust in collaborators. So in all these interviews, the people we talked to, they pursued federated learning with other collaborators that they already had existing connections with, or that they trusted to some degree. And so these people that are using federated learning know that federated learning in itself is not private, but they're still willing to collaborate with other organizations, and they trust that they will not misuse the system. And finally, clients are also concerned about the degree of control that they have over their data. So for instance, well, the main example I'll be using throughout this talk is opt-out guarantees through unlearning. And so if a client in the future decides that they wish to leave the network and they do not want their data to be used as part of this collaborative learning system, it's important to provide options that allow coordinators and data owners to efficiently remove data from a model. To give a bit more background on this interview study that we conducted, we compare the frequency of these 6 topics in both practice and in research. So these blue bars are showing the frequency of which these topics are mentioned in abstracts of search results from cross-silo federated learning. And then these orange bars are topics that came up during our interviews. One example of how a research and practice are misaligned is that traditionally in federated learning research, we focus on topics such as communication efficiency, computation efficiency, and learning from heterogeneous, statistically heterogeneous sources of data. However, in practice, many of the organizations that are using federated learning are actually, well, these are in a cross-silo setting. So they generally have the compute necessary to train a model, but they are more concerned about interorganizational concerns, such as setting up the system infrastructure, of incentives that are conflicting across organizations, and maintaining privacy. So in this talk, I'll be talking about a work on exact unlearning, which focuses on these 2 issues of systems and privacy. Great. So here the technical question is, how can we allow those coordinating federated or collaborative learning to efficiently and exactly remove the influence of a subset of fine-tuning data from a model? Okay. So to set up the problem, the unlearning problem is given a pre-trained model, we fine-tune this model on a combination of forget and retain data. After doing so, we want to unlearn the forget data, and so this requires us to edit the model in a way that the new final model that we obtain resembles a model that was only fine-tuned on the retained data to begin with. So here we have a diagram of what this looks like in a federated or collaborative learning setting, where we have data that is siloed across multiple clients or data sources. A subset of these are the retained clients, and then there are some forget clients that we want to unlearn. So here, forgetting or unlearning will be some operation that gives us a model that resembles the model from running this federated learning algorithm on only the retained clients. The concept of unlearning is not unique to collaborative learning. It's general to any learning algorithm, actually. So you could consider this to also be applicable to a centralized learning setting, where instead of learning over siloed data, we simply have some subset of data that is retain and forget. A natural baseline, a popular baseline for unlearning is approximate unlearning methods. And these are based on fine-tuning on the forget or retain data. So there are two main options here. You can perform gradient descent on your forget data to minimize the predictive utility of your model. Or you can continue running gradient descent on your retained data. These methods are called approximate because they are trying to minimize some heuristic objective. This is, say, model utility or KL divergence. But the key limitation of this is that they do not guarantee that the model cannot be attacked, and that there may be supposedly unlearned information from the forget set that you can still probe this model to obtain. The other alternative to approximate unlearning methods is exact unlearning. And so typically, exact unlearning involves retraining your model from scratch, or in our case, we are doing fine-tuning from our pre-trained model, so we are doing fine-tuning from that pre-trained initialization. But obviously, retraining over an entire data set or rerunning your entire federated learning pipeline may be prohibitively expensive. And so there are techniques in the unlearning literature to reduce the cost of unlearning based on storing additional checkpoints or partitioning the data. So for example, here is one baseline that you may be familiar with called CISA, which shards and slices the data so that when you want to unlearn a particular subset of data in one of these slices, you only need to retrain over the slices in that particular shard that come after the slice to unlearn. However, a limitation of CISA is that we ensemble these models at the end. So in order to run inference on this system, we need to store all these individual models in the ensemble. Okay. So there are a few baselines for unlearning. Our insight with this work is that we can use model merging or one-shot federated learning as a very natural baseline for unlearning. So the idea behind model merging is very similar to one-shot federated learning, or it is one-shot federated learning in that given multiple data sources, we are fine-tuning a task vector on each data source. So a task vector is simply the change in the model parameters that we get after fine-tuning versus at initialization. And then once we have fine-tuned multiple task vectors on each on one data source, we can combine them by simply adding them or averaging them together. And then this single model, so the single model tau nu that we get from combining the task vectors is cheap to store. And this is cheap to store because once we have learned all the task vectors and merged them together, we do not need to store the individual task vectors anymore. If we want to unlearn a particular task, then in the future, we only need to relearn the specific task vector that we want to unlearn, and then we can subtract it from the merged model. So model merging is a natural approach to unlearning. It's very cheap to unlearn a model compared to, say, centralized training. we only need to relearn the data that we want to remove, as opposed to centralized retraining, where we have to relearn over all the data that we are retaining. But there are a few limitations with model merging as is that make it impractical for unlearning and collaborative learning in general. So the first one is that when we are trying to merge a large number of models, utility degrades. So here are two prior works in the model merging literature. On the x-axis, they show the number of tasks that we are merging, so the number of task vectors that we are trying to average. And then on the y-axis, they show the performance of the merged model. And what you see is that as more models are merged, performance gradually degrades to that of the zero-shot model, so the model at initialization, before any fine-tuning. This right-hand plot shows several methods here, all with a downward trend. And these are all model merging methods that try to improve the merging procedure by doing something more sophisticated than naive averaging. This work in particular, localizing task information, proposes another method which allows us to retain high utility as the number of tasks increases. So I'll explain a bit more about this method. So this method, SIFT-Masks, localizing task information, adds an additional mask construction step to model merging. So as opposed to applying the multitask vector to all the tasks, this method constructs an additional mask for every task. The idea is that the multitask vector itself may not perform well, but it contains task-specific information that can be recovered so that you can produce a model that does do well for that particular task. And so the way these masks are constructed is based on a criteria that is a combination of both the original task vector itself and the merged task vector. So it prioritizes parameters that are important in the original task vector, so this magnitude term on the left, and also parameters which do not change much after being merged compared to the original task vector, so this condition on the right. And this lambda here is a hyperparameter that we sweep over multiple values, close to 1. However, a key limitation of this, so even though this does greatly improve performance, this introduces additional challenges for exact unlearning. Because as you see in this formula here, these masks depend on the multitask vector. So in original model merging settings, we could have just subtracted the individual task vector, and then that would give us exact unlearning. But now, when we apply these additional masks, we can no longer simply discard the mask and then subtract the task vector, because in these remaining masks, they still contain information about the merged multitask vector as well as the vector that we were trying to unlearn in the first place. So therefore, we need something different that can both give us improved performance and still enable exact unlearning. So I'll introduce another naive baseline that is also based on this idea of sparsity and masking. So this is a baseline called localize and stitch. It is also based on this idea of model merging, but it tries to merge sparse models together. So before the merging step, this method applies top K localization, top K masking to every task vector, and then merges the models. So we can extend this idea further by taking this multitask vector, as in this setting here, and then using the masks that were originally determined locally in this task construction and compression step. So this does enable exact unlearning because these masks do not depend on the merged model. And later on, we will show a comparison of how well this method performs against other baselines.
Kevin?
Yes?
So I'm slightly confused. What do you do once you get the mask? Like, what's the model you deploy?
Right. So once you apply these masks, then this mask is applied to the multitask vector, right? And then this merged and masked model is applied for the given task. So for task 1, you apply this first one. For task 2, you apply the second model, etc.
So you move from like deploying a single model on all tasks to number of tasks, number of models.
Right.
So why couldn't I just keep tau 1 to tau 4?
Right. So basically, the storage cost of these masks plus the multitask vector is going to be much smaller than storing all the individual task vectors.
So do you do some sort of constraint while optimizing for the mask to ensure that, like some compression? That's maybe what you're not, like, how do you do that?
Right. So in this prior work, the masks do not have a particular like sparsity constraint on the amount of sparsity. These masks are cheaper to store because they are simply represented as like a string of bits rather than like a 32-bit floats.
Okay, we will talk about that later.
We're still like, oh yeah. Oh, okay. Okay. So the goal of our method, so the goal in the method that we propose is to enable both model merging and masking, but while still allowing exact unlearning. So our method starts by initializing a global sign vector that is shared across all tasks. Then when we do local fine-tuning, we constrain the task vector to agree with the signs of the global sign vector or to be 0 otherwise. And so what this results in is individual local task vectors that all agree on their signs or are 0 otherwise. And then we merge these into a global model, and then we can apply, and then we obtained masks through this sign-fixed fine-tuning procedure, and then we can apply these masks afterwards in the same way that we applied it for the other methods as well. And then to unlearn, we can simply delete the mask, and we subtract the task vector from the merged model. And then the critical part of our method is that the masks that are generated locally only depend on a combination of the global sign vector and the local data. So there is no dependence on this global model after merging. Right. So now I'll talk a little bit about the experiments that we run to evaluate these methods. So there are 3 metrics that we are evaluating. One is utility before unlearning. The second is the compute that is necessary to perform unlearning. So even though I mentioned that some methods are not amenable to exact unlearning, they actually just have a very high cost for exact unlearning. So we'll evaluate that. And then third is the storage cost of all of these methods. So we compare a few baselines. So there are 2 naive baselines for this setting. So the first is model merging, and the second is centralized training. So we simply pool all the data and we train a model. And then to do unlearning, we will just retrain using only the retained data. And then we also investigate 3 other merging and localization methods that are applying this merging and masking pipeline that I described earlier. And then we also test multiple text data sets. And here we assume that the data from these data sets is naturally distributed across multiple data sources that we call tasks. And so each task is essentially a different data distribution in terms of the inputs and labels. But these tasks are all similar in the sense that, say, for example, for tofu, we are answering questions over some set of fictitious authors, and each author is one task. For Cent 140, we are doing a sentiment classification. And so each task here corresponds to data from a different real-world person account on Twitter, and may have a different distribution of the labels. These other data sets are similar, so each task is simply a different natural source of where the data is coming from. Okay. So first we compare utility of model merging versus our method, which we call SIFT-Masks. So here, as we saw before, model merging degrades as more models are merged. For this tofu task, adaptation is very important. So the pre-trained model starts with 0 utility because it has no knowledge of these fictitious authors. And so fine-tuning is necessary for good performance. And therefore, there's a very huge gap after performing model merging as we scale the number of models. Similarly, for other data sets, there is degradation at scale, and our method retains good performance at a large number of models merged. So next in this plot, we also continue to compare the utility of models. Here we are showing that our method, SIFT-Masks, enables better local model recovery. So by applying this masking step to the merged model, we can obtain a model that is similar in distance, that is close in distance to the original task vector itself. So this distance is what we are comparing in this table here. So for example, for just model merging alone, we compare the distance between the merged model and the local model. And so this is a large distance and has low performance. Other localization methods, so other methods of generating this mask, can reduce the distance to the original local model, but still achieve low performance. And then our method also reduces the distance from the local model and achieves the best performance out of all of these. Next, we analyze the unlearning cost of all these methods. Yes, go ahead.
So in the previous graph where you compared before this actually, what's the non-collaborative baseline performance if you just use tau-wise for each task?
Non-collaborative. Right. So
that should be just constant.
Right. It's right. So it's just constant, like 1.0. Yeah. Like as you see, like in these prior works for model merging, the performance of the fine-tuned, just the multiple fine-tuned models, if you apply each local model to its individual task that it was trained on, then this is...
You're normalizing with that performance essentially here, while plotting the y-axis.
Right, so we don't normalize performance in this plot, okay. But the idea is that whenever you perform merging, your performance will degrade relative to applying the local models to their individual tasks.
So should I view it as like some memory benefit for like the server as opposed to everyone keeping their own model? Is that the...
Right. So I guess like this is a bit unsatisfying in that like when you combine these models, when they collaborate, you do not increase your performance beyond what you had originally, but there is benefit in terms of compression across multiple tasks. Right. So next we compare the unlearning cost of these methods. So on the x-axis, we're showing the number of fine-tuning steps that are necessary to do unlearning. So our method has the same unlearning cost as regular model merging because we are simply fine-tuning over the one task that we want to forget and then removing that task from the merged model. Compare this to centralized fine-tuning where the number of fine-tuning steps here is basically showing training over all the retained data. So at this first point, you are starting with the pre-trained model, and you have to do a significant amount of fine-tuning before you recover performance that you had before. And then also, other methods for doing this merging and masking approach have very expensive unlearning costs because the masks depend on the merged model. And therefore, in order to do unlearning, you would have to regenerate all of the individual task vectors and then regenerate all of the individual masks so that they do not have the influence of the unlearned task. I think we're short on time, so I'll skip over this slide.
Yep, like 2 minutes.
Okay, yeah. So in conclusion, we are trying to develop a method that does well in terms of this three-way trade-off of unlearning cost, storage efficiency, and model utility. And so we showed that existing methods fall short. So for example, exact centralized retraining is inefficient in terms of relearning. And model merging falls short in terms of utility. So we tried to develop a method that allows us to get exact unlearning, but also has the same computational cost as model merging, but also retains the high utility of model merging with additional masking. Yeah, so I think there are a few very interesting directions based off of this work. So our method is primarily a change to the learning algorithm that enables unlearning to be exact. So there are other ways to change the learning algorithm that may make models more amenable to merging and localization. There's also an ongoing area of work that tries to improve the merging and masking methods themselves. And then there are also alternative architectures that we can explore that also leverage this idea of combining multiple models. And then also in our setup here, we do not try to make these models private. Privacy is, we take a different view on privacy in that we can exclude models through unlearning. And then here we also consider only unlearning single tasks that are associated with a single data source. But there could be more flexible models of what data we want to unlearn. Okay. Yep, thank you.
Any additional questions for Yusuf? Sorry, Yusuf comes up. Any additional questions for Kevin? Yeah.
One question.
Yes.
So you mentioned that as the number of tasks grow, the accuracy degrades, right? Of
Yes.
the model. So at what point does it become so bad